So today we will be discussing the lecture 3. The contents of the lecture 3 are images, pixels and geometry. So in the last lecture we have already talked about what is the image. Image is a collection of pixels. What is a pixel? Pixel is the smallest element of a screen. Okay, and then we'll talk about here the geometry. So first of all, light. Okay, we all know what is the light. Light is a form of electromagnetic radiation or electromagnetic energy that travels as wave, and that can be characterized by either their wavelengths or their frequency. So basically, if you want to calculate the speed of the light, we have to multiply the frequency and the wavelength of the light. We know that light is actually very fast. It can travel up to 3 into 10 to the power 8 per second. So it's actually the fastest anything that you will ever find. So here we have different types of wavelengths. We have the gamma, X-ray, and in between gamma, X-ray and the heat and radio, we have the light wavelength. So in the light wavelength is actually divided into 3 colors: blue, green and red, and starts from 350 and up to 780 nanometers. So this is the range of light wavelengths. Now, as you can, we have already studied that using these 3 colors, the primary color, red, green, blue, we can actually construct any color possible, up to 60 million colors. Now, the question is that why we are actually learning the definition of light. So because when we actually drawing a picture, if you remember, we're actually using an electric gun to actually shoot different types of different colors of light into the screen, and there is a phosphor screen that actually what is the word I forgot? Reacts. Yes, that reacts to the light, and then we can actually see different images. Okay, so here is the chart of electromagnetic spectrum. Okay, so just to give you an idea that out of all this whole spectrum, okay, here we have a football field in the terms of 10 to the power 3, 10 to the power 2. Here we have a baseball, and if we keep going on, okay, here we have a subatomic particles. So out of all of this, okay, all of this, the light wavelength is actually very small. So in computer graphics, we actually do not deal with the wave nature of the light. Okay, that is not our concern, how the physics work. Okay, we are concerned with different light sources have a fixed rate of intensity. So whenever we are actually designing a system or graphical system, we actually have to be concerned with how we actually use the light. So we know that light travels in a straight line from one source of emits energy from a single location at one or more frequencies equal to all direction. So basically, if you think of the sun, okay, whenever the sun shines, the light actually goes in all the direction from that. So if you're handling a light object, okay, an object that actually emits the sun, okay, so or we can say that if you want to use a light bulb or any sources that actually represent the light, okay, you have to keep in mind these properties of the light, that how the light actually work in real life, so that you can actually implement those in the your graphic system as well. So more complex sources such as light bulb can be characterized as emitting light. So yes, light bulb is a little bit complicated than the sun. And then we have lamp. If you have a table lamp, you will see that it actually only enlightens a small amount of area. So we'll gradually see that how to actually handle the different sources of light. Now, first of all, this is an image, human eye. Okay, in the human eye, we have this visual system where light enters the eye through the lens and cornea. So this is our lens and this is the cornea. Whenever we look at an object, light actually enters in our eye through lens and cornea, and a transparent structure that protects the eye. So these are the transparent structures. The cornea is that protects our eye from getting any harm. The iris opens and closes to adjust the amount of light enters the eye. So this is the iris, as you can see. Okay, so it actually controls the amount of light that can enter. The lens forms an image in a 2D structure called retina. So this is our retina and this is the lens. So whenever you look at an object, this lens, okay, forms an image of that 2D object, 2D structure in our retina. Okay, The rods and cones are light sensors and located in the retina. So in the retina, we have different type of spatial sensors cell. Okay, so this cell, they actually reacts to light. And whenever you actually look at an object, okay, their image is being formed in your retina that actually reacts to light, and they are excited by the electromagnetic energy in the range of 350 to 700. So that's why we actually first studied that the range of the color that we see is from 350 to 950 saying. So we have this range of electromagnetic, that 350 to 780 nanometer. So basically, whenever you look at an object, if the object emits a light, that the range of the wavelength is from 350 to 780 nanometer, those lights actually falls onto our retina and we can actually see the object. Okay, and remember that our retina, there are two different types of cell, rods and cones. Okay, they actually response to light, and then these rods and cones, they have a range, that range is 350 to 780. What does this mean? That if a light or wavelength come whose magnetic energy in the range of more than 780 or less than 350, we will not actually see the object. Same goes for the sound. We know that human has a limited range of sound. Okay, if
20 to 20,000 hertz.
Thank you, 20 to 2000 hertz. So if there's any sound that has more than 20,000 or less than 20, we cannot actually hear it. Okay, now the rod cells that you see are low level light. That means we actually use rods for watching in the dark, okay, in the night vision. And the cones are actually high level light, the day vision. So we, using the combination of these two, we can actually see in the night or in the day. And you see the cones are actually not useful in the dark, and there are three types here. We have RGB, red, green and blue. So in the dark we can only see black and white. We cannot see colors in the drug. At best we can actually see gray images, but we cannot actually see red color, any colors in the night. Now in the human visual system, okay, first of all you have the fovea. This is the high resolution area in the retina. So here, if you forgot, this is the retina, okay, this part. So in this retina we have different type of mechanisms. First one is called fovea. This is a high resolution area in the retina. Cones are mostly at the fovea. So the cone cells that actually represent, you see the cone for high level light, day vision, the RGB, they are actually in the fovea, and rods are all over the retina. So the rod cells that helps us to watch in the dark, they are spreaded all over the retina. The optic nerve, okay, what is the optic nerve? This one is the optic nerve. Okay, the optic nerve is the signal processor that sends the image to the visual cortex in our brain, where high level functions such as object recognition are carried out. So first we look at an object, the light actually comes to our eye, okay, they falls onto our retina, and from the retina we have we have a fovea, and we have the rod and cone cells. And from the rod and cone cells, what happens, we actually, the signal actually being transferred to our visual cortex in the brain using optic nerve, and there we use a function called object recognition. So if we see a human, we can say this is a human. If we see a mobile, we can say this is a mobile. If we see a tree, we can say this is a tree. The resolution of our visual system is the size of the object we can see. So basically, if the object size is larger, the resolution is large. If the object size is small, the resolution is small. So if you look at a object that is actually far away from you, okay, in that case the object size will be very small, okay, and that means the resolution is also small. Just think, if you look out of the window and if you see a plane, the plane actually seems very small, okay, just like you can cover it with your one finger, okay. So that doesn't mean that actually the plane is small, right? We know that just because the plane is far away, the resolution of the plane is less, and that's why the size is also less. And then if you look at something very close, you see we can calculate this is actually very huge because the resolution is also huge. That depends on the distance between you and the object. So here we can say that is if where more technically it is a measure of how close we place 2 points and still recognize that there are two distinct points. Our eyes do not react uniformly at different wavelengths. It does not have the same response to a monochromatic single frequency red light as to a monochromatic green light. If these two lights have emit the energy at the same intensity, they would appear to us have different brightness. We are more sensitive to the green light and least to red and blue. So basically, even though they are the three different primary colors, our eyes actually reacts or more sensitive to green. So if there is a green in somewhere in the screen, even though both of them have the same intensity, we'll actually think that green one is more brighter. Okay, so why we actually are more sensitive to green? So if we actually go back and if we actually see here, you see green is in the middle. This is actually kind of perfect for us. Blue, that is the minimum, and red, that is the maximum. So these two actually in the range of max minimum, and green is the range of average. So our eyes are actually more sensitive to green light. And then the objects. An object is a self-contained thing that has a structure. We have studied the definition of object in our C++ course as well. Okay, let me pause for 1 minute. So as we're talking that
Assalamualaikum.
we have already discussed that in the what is an object in our other courses as well, but the graphical object and the object oriented object are not the same thing. Here we actually use objects are primitives and it has attributes like line, style, color, surface, texture. Okay, and it has points, lines, polygons. It can be free from surface, etc. So that anything that you see that have a that has its own shape and own properties, okay, we can call it an object. And connectivity relationships and positioning data that describes how the components fit together. So basically we'll have a self-contained structure that has its own properties, number one. So own properties, that has its own behaviors, and the connectivity relationship between those behaviors. So let me give you an example. So let's assume that in your graphical system you want to represent two objects. First object is here a small tennis ball, another object is a box. So what is the difference between them? First one, the as a tennis ball is actually a circular object, okay, and a box is actually not circular. Okay, it is combination of polygons and different surfaces. Now a box might be from different shape, but the one thing, it will be a collection of, it will be a polygon. Okay, now second thing, a ball, it has a property that it will roll. So whenever you have a ball in your screen, if you have played different games using a ball, roller ball, let's assume, okay, so what you will see that the ball has a property, it will roll. Okay, but the box, it will actually not roll. So these are the properties of an object. Then there's another object. Okay, you can actually open a box, okay, but you can actually open up an tennis ball. So these are some examples. Okay, so whenever we actually represent any objects, okay, it will have some unique properties of its own, and there's a relationship, there will be a relationship between them. Now what is a virtual environment? This is actually a little bit more interesting, the virtual environment, because nowadays with the improvement of the graphical user interface, okay, what we're actually doing, we are actually making the animations, the graphical system more and more realistic. Especially if I talk about the simulation or the games that is being released. Okay, if you see the environment that has been made there, they look so realistic if you have a good graphics card. I will show you in video very soon. So first of all, let's see the definition. Virtual environment is a set of independent objects following laws and behaviors that define a world or virtual environment. So we're actually trying to recreate the world. Virtual environment have content. Okay, just like suppose if you want to draw a virtual environment of a field, so it will have the same contents of the field. It will have different dimensions, metrics, extend the boundaries, and will have the dynamics. Okay, consist of rules of interaction. So different objects will interact between them. So the more contents and the more geometry and dynamics you apply into your virtual environment, the more realistic it will be. Okay, and nowadays we actually see a lot of realistic virtual environments. and then we have actually we'll discuss the content of the virtual environment. So before going to the description, let's watch a video. Okay, so let's see how video games actually improved over time. Keep your eyes on the age timeline as well. If you just focus on here, you can actually see the pixels being generated. Okay, so let me interrupt here a little bit. So you see this game, Max Payne in 2001, it was actually, it got a very famous because it was the first time when the game developers have successfully developed a virtual environment that actually looked almost like the real life. So you see, if you look at the environment, yes, it's all obviously cartoonistic, but still this is the first time that we have developed a gaming environment that almost look like a real life environment. So it actually got very famous and one of the most popular game of that time. And then gradually we kept improving.
Dr. Freeman, I presume. You better hurry. The Combine can be slow to wake, but once they're up, you don't want to get in their way. I'm Alex Vance. My father worked with you back
in this picture, okay, in this video, as you can see, you see the lift is actually is an object. The person that is talking to you is also an object, okay, and everything you see here, they actually having their own properties. The lift is actually working like a real life. So that's what I was actually mentioning, that whenever we have a virtual environment, the objects that we have, the contents that we have, okay, they will be actually almost similar to real life. They will have their own properties, okay, just like the real life.
Black Mesa? I'm sure you don't remember me, though. Man, a few words, aren't you?
You see, he just pushed the chair, okay, so that means there is a physics there. So I will not actually continue the whole video. If you want, you can watch it later. Let's just skip to the last part of the video. Okay, one of my favorite games is here. So let me just go to skip to. So this is a game of 2015, and after that, the next one will come.
Una caseta médica.
Okay, you see this game, okay, Horizon. If you look at the user graphics and the environment, it's almost looks like realistic. And you will notice when the character is walking on the water, there will be splash of water. So the environment is so perfect that you will almost feel like you are actually there. So anyway, that's actually brings us to the end of our video. So let's go back to our slide. So that was actually we're talking about whenever we're talking about virtual environment. Now the next thing is, so as you have seen in the video, that at any moment of time, an object has a description and a state. So what is the description? It's that the information about the object's geometry, substances, potential behavior. So when the character was in the Horizon game, when the character was actually walking through the environment, it was actually interacting with the environment. Okay, whenever it was actually walking through the land, it had a different sound. Whenever it was walking in a water, it had a different sound, different state of the object in relation to the rest of the environment. Okay, and an actor is actually a special set of objects that can initiate an interaction. So if I think about a game, so an actor can be the character that is walking, or that you are playing in the game. And it can be like, it can initiate an interaction with another object or actor through information exchange. And then it can be a participant, a human operator that has a visual representation within the environment or controls the behavior of one of the actors. So there are many ways we can actually define actors and the environments. But in short, okay, whenever we're actually defining this virtual environment, okay, there are a lot of parameters, there are a lot of objects that you need to control, and all of this object will have their own characteristics that you need to define. Now that's why you see it becomes actually very difficult. Just think of a racing game, simple racing game. Your car is racing through the road. Now, first of all, if you remember in the video you have seen the previous racing games, actually the roads, whenever you're moving through the road, okay, the map or the roadside, okay, the buildings actually change very fast. So that is one thing you need to do, that whenever your car is actually moving through the road, your buildings need to change, and there need to be actually have a presentation that actually makes you think that you're actually moving for front. Okay, if you remember the game Flappy Bird, okay, in the Flappy Bird there is some same way, whenever you're actually clicking the screen, a bird is actually going up and going down. Okay, and there was actually a graphical animation behind the screen which made it look like that the bird is actually moving front. Okay, where in the whole time the bird was actually in the same place. So that is actually the characteristics of virtual environment. And the virtual reality, we have heard the term VR recently, especially in VR the participant lives in the virtual environment, sees with the eyes of the actor and feels as the being the control of the actor itself. At the end of the class I will show you a VR video which will actually makes more sense, and you will see VR is actually very funny. I have personally experienced VR and it was actually very nice experience. So in the VR, okay, even though we know that we are actually not in the game, but whenever you actually put on the display, you see the glass they are wearing. Okay, when you actually put on the display, okay, it actually covers your whole senses, even the sound. So we know that we have different type of senses. We can hear, we can see, we can actually feel with our skin. Okay, so we have different type of senses. So what happens when you actually use a VR, it takes control of your eye, it takes control of your ears. So actually you feel like without the senses, you actually feel like you're already there. So it's actually very fun. I will show you a video. So here what we do, we actually, the participant movements are captured by a tracking system. So what happens when you actually capture the movement, so if you look right, it will show you one type of animation. If you look left, it will show you another type of animation. So it will give you the feeling that you are actually in a real life environment, and whenever you're looking right, you're seeing the right side, you're looking left, you're seeing the left side. Now whenever we are actually forming an objects, okay, it can be defined and approximated by specifying the position. So in the space of various geometric primitives such as points, lines, and polygons. So in simple terms, if you actually want to specify, or if you want to actually draw an object, we do that using a combination of point, line, and polygons. So for example, if you want to draw a line in your environment, it will define by two vertices. That means there will be 2 points and line will be connected by from the 2 point. If you want to draw a polygon, it can be defined by an ordered list of vertices. And if you want to actually draw a sphere, it can be specified by 2 vertices, the center and the point to circumference. So each of these geometric shapes has their own property, and whenever you are actually trying to represent these shapes into our environment, we have to follow these properties, the vertices, the circumference, the radius, and using the combination of these properties we can actually draw different objects. So if you remember, if you want to draw a box, what you can do, you can just draw multiple lines, and if you just join multiple lines, okay, you will have a box. So this is one example. Another example can be here. Let me show you this one. So if you want to draw an actually image of this box, okay, so what you can do, you can actually draw define 5 or 6 points or vertices, and you can join the line, then you'll have this object. Or you can do this one, but you see this one is actually not completed. Okay, we'll come back to this one later. So let's go back to our slide. So now whenever we are actually seeing an object, you have to remember image and object are not the same thing. So here is a perfect example. So here is a person B, he's looking at an object, and person C is looking at the same object. Now person B, he will see the object in this way, and person C will see the object in this way. So now this image of this object, okay, the visual representation that you have, it doesn't actually represent the whole object. As a human, we know that if you want to actually get the whole object, okay, it has a lot of images depending on the position of the perspective of the viewer. That means if you look at from this side, you see B. If you look at from this side, you will see C. So if you want to get the perfect idea or the visual presentation of an object, you have to look at from all side. Okay, so an image is not an object. Image is depends on many things, from which side you are taking the image, okay, from which corner you are taking the image, the angle, the side of the image. So the view actually forms the image is 2D object. Now, one thing that we all understand, that here these two images, none of them actually represent the object in the same way. So whenever we are actually designing an environment, we have to keep that in mind. The viewer, okay, if somehow he looks from one side and he can see the whole object, okay, it will not make any sense. For example, we are also looking at top view. Top view means we are looking from the top. That's why we can also see the B, the C, and we can also see the rooftop. So if you are actually looking or take a picture from the top, you can actually see the bird's eye view of those two sides. So just remember one thing, that image and object are not same thing. That's it. Okay, if you take an image of an object, it depends on from which side you are taking the image, which angle, and so on. There are a lot of parameters it depends on. So image formulation is actually two-dimensional, the one I have just talked. So suppose this is a camera and you are taking the image. So it actually depends on the viewing angle. And also it depends on the light source. You see here, if the sun is in this side, if you take the image from this, you will have actually dark side in this one. Without light sources, the objects would have been dark. There would be nothing visible to the image. So whenever we are taking an image, we have to make sure that the light source is working properly. And we also have to keep that in mind, the effect of the light. Then the light from the sources strikes various surfaces of the object. Now, we will actually try to develop some Blender application. Today, I will also show you another video of why we actually covering these light sources. Because whenever we are actually generating an animation in the Blender, okay, the effect of the lights actually changes a lot. Okay, so let me just complete this slide, then I'll go to the video. So light from the sources strikes various surfaces of the object, and a portion of the reflected light enters the camera through the lens. So basically the light will reflect here, and a light will go here, it will reflect, and this light will come to the camera or our eye. So here, let's go to the video. So here is first sample video, let's watch it.
So today's video is a really quick tip to get you that bloom look that you see in Eevee in Cycles. Let me show you how to do it. All right, so if we happen to look dev, this is the Eevee view. Of course, we have this nice bloom, but here in Cycles, you don't get that viewport bloom. It's just flat, and you just see those reflections. So how do you do it? First off, in Eevee, lights are very sensitive. So these are very, very bright here in my emission, but you can bring it down, see at like 1 point, you could still see glow. So just remember in Cycles, they need to be pretty bright. So I put my strength at 30 for all these emissions, and it needs to be an emission shader, or it can just be like, say, a light is shining on something that's very bright in the reflections. It doesn't just have to be emissions. Because this is Cycles, it is photorealistic. All right, so all you have to do is hit render and render image. And once you render it, you have to hop over to the compositor. So right up here, you'll see compositing. So now you have this. So once you render it, you'll just see this. This is the rendered object you have. It's not object, rendered image. So you can't see anything. You have to Shift A and type in viewer. Once you have this viewer node, hit the image and bring it to image. And now you have your background. So to get the bloom, you have to Shift A and type in glare. Right here, and put right between these two nodes. And you'll see, bam, this happens. It's pretty ugly. And that's because we're on the streaks. Here in Cycles, you actually have multiple options in your streaks and things like that. So if you just want the regular,
here, as you can finally see, you see in these different lights, they're actually creating a composite effect, and which is actually very cool, right? We can all agree this actually looks very nice, but this doesn't actually count very easily. All of this light, you have to make a lot of renders. Now I know now many of this doesn't make any sense, like, sir, what is a render, what are these controls? Okay, don't worry, we'll learn them step by step. But for now, let's focus on what he have created here. So as you can see, there's actually a very nice lighting system where there are different lights that are actually in different intensity, and all of them actually making a composite effect that actually looks very nice to see. So in this video, we will also see that if the light changes, what effect it has on this object. Okay, so let's start.
Now a widget has appeared. It's this yellow dot here. Let me click it and drag it. And by taking a look at the shadows of the two objects here, you'll see that I'm changing the rotation of my sun lamp by clicking and dragging that dot. I'll come back to this dot later, but for now let's switch over to a spot lamp, which also features this dot, but also this arrow here. And when I click and drag the arrow, you see that I'm opening and closing the cone of my spot lamp. Now let me switch over to area lamp. It also has two types of widgets. One is invisible right now. The other one is, of course, the yellow dot. And now let me take a closer look on the yellow dot by clicking it and dragging. And you see that the rotation of my lamp object or my light object here jumped abruptly. And when I move my mouse over here towards the cube, you see it's jumping again. And that's because this dot is actually tracking the surface of my scene. And that means basically that I can use it to point and shoot. So I can click and drag it anywhere I want my light to shine onto, and it will automatically shine in the right direction.
So you get the idea that depending on the different types of light, the object will be shown in different way. So first, if you go back here, so this is actually, assume this is our light source. It might be a sun, it might be a lamp, or it might be a light bulb. Okay, and you can
yellow
see
dot
when you
here,
actually move the light
by
objects,
taking a look at the shadow,
you see the shadow actually changes. So basically, we have introduced the effect of shadow using light. Okay, or we can also change the light to actually in cone shape. It's almost like a torchlight. So you're actually moving a torchlight. So you see in different games, sometimes we give the character a torchlight so that it can actually see the environment and so on. So all of this can be done using the effect of lights. So this is actually very interesting how the light work. Now, so displaying image, whenever we're actually showing image, we can actually use different way. We can use a wireframe image, or we can use a shaded image. So we'll look more into the details, what is a wireframe and shaded. But in short, you can see the idea that in the wireframe image, we have like different, it's like almost, how should I say? It's like a structure. This one almost looks like a skeleton of the image or structure of the image. And this is like a complete image. So now the question is, it is extremely difficult to actually create reality on a computer display. So if you want to actually represent this box, okay, so the problem happens that sometimes we cannot actually represent it properly. Though, here you can see all the corners, this one, this one, this one, this one. But if it's a solid object, okay, if you look it from this side, you'll only see this side. Just imagine, suppose you have a huge mountain and you want to actually represent the mountain in the computer screen. So it actually becomes very difficult. And if you look at from one side, you actually don't understand whether this is a mountain or a wall. So the texture has to be very high. So what can we actually do? Just imagine this character. Okay, this is a character from Deadpool, and you want to actually represent this character into the computer screen. So even though you are actually using the proper color composition, this actually, those of you who have watched Deadpool, you can actually identify, oh, sorry, this is Deadpool. Okay, but still, we know that this is actually don't look much like Deadpool. Okay, so the monitors can actually, yes, it's all, and for this one is Spider-Man. If you look at the top, we have the Spider-Man and we have the Deadpool. Okay, two characters. How I can actually identify this one is Deadpool? By seeing the sword, okay, behind his back and the screen. And here the Spider-Man I can understand by his blue and the spider. Okay, so the monitors can be bought as a piece of graph, thought as a piece of graph paper, and we can split it into different pixels. And these pixels, squares are called pixels. We have studied in the last chapter what is a pixel, how we draw pictures, and it can change colors. So to actually represent any object into the screen, we need higher resolution. Okay, the small number of pixels are not enough. Okay, we need higher resolution. So the more high resolution, the more number of pixels we have, the more clearer the object becomes. Then to identify pixel, we have actually use axis. So axis, that means x-axis, y-axis. Okay, the vertical axis are from left of the screen, and from the downward left to the top. The horizontal axis at the top of the screen towards the right from the left top. So x, we already know what is x and y axis. The origin. Well, the origin is where the x and y axis intersect with each other. So if I actually, you know what is origin, but let me just draw one basic diagram. So you say if this is the x, y axis, and this is the x-axis, so they intersect in this point, so we call this origin. So it might happen they might intersect in this point, so again we'll call this origin. Okay, it doesn't matter how the shape is, whenever they intersect, we'll call that one origin. So that's how actually origin work. Now go back to the slide. So we have the origin, we have the coordinates. So with the coordinates are the points of x and y. We will see a map of the coordinates very soon, and we actually use these coordinates to actually draw a pixel. So here the position of the pixel is then the pair of numbers of showing the distances x-axis and y-axis, and this pair of numbers in brackets called coordinates. So if you have actually drawn any graphs, you know that first whenever we are drawing a graph, we actually point some coordinates, that 2 2 3 3 4 4 5 5, and then connecting those coordinates we actually draw the graph. Now so here we have a monitor, okay, computer screen monitor. So what we will do, we'll use this one as an origin, 0 0. So this is our 0 0, and this is our x-axis, and this is our y-axis. Now I will show you the math now, so be attentive a little bit more. So we have, it is 0 0, the origin, we have the x-axis, and this is the y-axis, and we have the resolution of this image is 639 into 479. Why 639? Because in the x-axis we have 639 dots, and on the y-axis we have 479. So if I multiply both, we have total 3,07,200 pixels. Now using this 3,07,200 pixels, we'll actually draw and we'll image, and we'll also calculate how we can draw the image. So first of all, to draw an image using pixel, we first have to identify which pixel to draw. So basically that means if I ask you to draw an A, so you first have to identify where should I start the A, from here or from here or from here. So you have to first identify from where you should actually draw the object. So if I actually show you in the screen, so okay, wait. So if you want to draw the A here, or whether you want to draw the A here, or whether you want to draw the A here. So first you actually have to understand, know from which pixel you should start. Okay, so to calculate this pixel address, okay, what we do, we actually use this math. So let's start with a simple one. So let's assume we want to draw one single point, 4 3. Okay, now the question comes, where should I draw the 4 3? So normally it seems like okay, from 0 move on to the 4 to this and 3 to this, right? Whereas if you use the graphical representation, this is actually very simple. From 0 0 move to the 4 axis, to the 4 1 2 3 4 here, and to the y-axis go to the 3. But in terms of pixel, okay, there are a lot of pixels here. This is the first pixel, this is the second pixel, third pixel, fourth pixel, fifth pixel, sixth, seventh. Okay, if you remember, whenever we are drawing a pixel image, what we do, we actually use a line. So that means our electric gun start from here, and it will actually go up to this way. After finishing this line, it comes to the second line, and again it draws the second line. After finishing the second line, it goes to the third line. So the electric gun has to know that which pixel to draw. So instead of calculating in this way, that this is 4, this is 3, it has actually a better approach. So what it does, it actually keep in mind that which pixel to draw. So to the electric gun, okay, if you want to draw 4 3, what it does, it calculates, this is the first pixel, this is the second pixel. So first, second, third, fourth, fifth, sixth, seventh, eighth, ninth. So it actually remembers that I have to draw 4th pixel or the 5th pixel. So what we do, first we calculate the value of Imax. So what is Imax? So Imax basically the most number of dimensions. So here, as you can see, it starts from 0 to 9. So basically we have 10 dimensions. Why? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So if you start counting 0, 1, 2, 3, up to 9, you will have how many pixels? You will have 10 pixels. So the value of I is 10. And now the point you want to draw is 4 3. So the value of I is 4, the value of J is 3. Now how we calculate the pixels that you need to be drawn? So we actually use the origin, that is 0 0. The address of value of the origin is 1. So address 0 0 plus j into x I max plus I. So as I said before, the origin is 0 0. That means 1. This is the first pixel. Then what is the value of j? The value of j is 3. So we've used 3 here. What is the value of I max? So multiplied into I max. The value of I max is 10. Plus what is the value of I? It's 4. So this is 35. So that means in this monitor, if I want to draw the point 43, I will draw the 35th pixel. And that's how it will actually remember. We'll see some more examples, don't worry. So let me clear the screen. So here we can now discuss in details how the theory works. So pixel is the smallest addressable screen element which can be controlled. The monitor can be visualized. The monitor can be visualized as one-dimensional array of pixels. So we can calculate pixels using address 00, that is the first pixel, plus j into I max, the maximum number of pixels you have in your, or the, I can say the maximum number of pixels you have in one case. And then we can add I. Now, I max is the maximum number of pixels in a row, remember, not in a column, in a row. So 0 less than I max, and j max is the maximum number of pixels in a column. So using this formula, I have just shown you how we can actually calculate a pixel for a monitor screen. Now here there is another 2 problem. Okay, practice this at home, and if you, in the next class, we'll discuss the answer of this 2. So finally, we have the last slide. Okay, so I guess all of us, you are tired. I'm also tired from speaking. I have been taking 6 classes from the morning. So here in the geometry, as you can see, we have points, we have lines, we have circles, ellipse, and curves. So in summary, whatever you want to draw, here there's a picture of polygon, a line, and a circumference, and polygon, and curve. So all of this is actually a combination of points or lines or ellipse or curves. So any object that you want to draw in your environment, in any image you want to draw, you will actually need this geometry. So that's why we actually first learn how to draw this geometry. Then we can actually represent any image in the computer screen using the pixels. Now we will see one last video, okay, or we will see the video in the next class of how actually an environment reacts. And today